Let's get into some more details about these logarithmic functions. So say we have our exponential function, f of x, and let's call that b to the x. Then the definition of the logarithmic function is the inverse of this function. So log base b of x, this is how we notate the logarithmic function. We put log and a base, is the inverse of the exponential function b to the x. And in English, we say that this is log base b of x. Now remember, inverse functions switch x and y values. So if f of x equals y, then that means that x equals f inverse of y. And I want to write this out using the fact that f of x is b to the x and log base b of x is f inverse of x. So f of x is b to the x, so b to the x will be equal to y. And if that is true, then x will be f inverse of y, and f inverse of something is log base b of something. So log base b of y. Let's do a specific example to make things a bit more clear. So for example, we know that 2 to the 5th is 32. In this statement, b is 2, x is 5, and y is 32. Now looking back, we said b to the x is equal to y. That means that x is log base b of y. So let's go ahead and copy down what x, y, and b are, but in this statement. So x would be 5, so 5 equals log, and now we'll put b here. B in this case is 2. And here we put y, which is 32. Let's do another example of applying this definition. So we know that 3 to the minus 2 would be 1 divided by 3 squared, which is 1/9. And so x would be negative 2, b would be 3, and y would be 1/9. So that means that negative 2 would be equal to log base 3 of 1/9. The way that I personally like to think about this is if I have some exponential statement here, such as 3 to the minus 2 is 1/9, I'm moving this 3 over with a log, so that's how I get this. This 1/9 stays here, and this negative 2 drops down. Now I think I'll make the remark here that all of these statements which I've written are true. That is, these 4 statements of 2 to the 5th being 32, 5 being equal to log base 2 of 32, 3 to the minus 2 equal 1/9, and negative 2 being equal to log base 3 of 1/9. All of these statements are true. The statements that are of the form on the left-hand side here, that is these two, these are called statements in exponential form. And these statements on the right are called statements in logarithmic form. And it's important to be able to convert from one form to the other. What we've done on this page is convert from exponential form to logarithmic form. So specifically, if you had the example of convert 2 to the 5th equal 32 and 3 to the minus 2 equal 1/9 to to logarithmic form, then you would do the exact work that we just listed. You would say 2 to the 5th equals 32, and then you would write that 5 equals log base 2 of 32. You can phrase this question in a different way, testing the same principles. So you could say something along the lines of convert log base 2 of 32 equals 5 and log base 3 of 1/9 equal to -2 to exponential form. And the solution of this would be the exact same work, but in reverse. You would start with log base 2 of 32 equals 5, and we would take our base b and move it over towards the right, and we'll take this and raise it upwards, and we get that 32 is equal to 2 to the 5th power. Try doing the exact same thing on this statement, and you should obtain that 3 to the -2 is equal to 1/9. Now that we have some basic ideas understood, let's go ahead and write out some consequences of the logarithm being the inverse of the exponential. So since the logarithm is the inverse of the exponential, the following statements will be equivalent. Y equals log base b of x is equivalent to b to the y equals x. There are a few different ways to say is equivalent to that are common in mathematics. You could say, well, is equivalent to. A lot of times we say if and only if. And for short, sometimes we just put IFF to mean if and only if. But any way you want to say it, what it means is that this statement of y being equal to log base b of x is true if b to the y is x, and b to the y being x is true if y equals log base b of x. Also remember, for the definition of exponential functions, we require this b to be greater than 0, and so we'll make that requirement here as well. We'll also require that b not be equal to 1, because if you take a look at the exponential function b to the x, where b is 1, you just get the function 1 to the x, and 1 to the x is 1 for every x. So this is just a constant function. So we won't call this constant function an exponential function. So b has to be larger than 0, and b cannot be equal to 1. And that means this b as well. Cannot be equal to 1 and has to be greater than 0. Another consequence of the logarithm function being the inverse of the exponential function is that we can determine what the domain and range of the logarithm function is. Remember, the domain of the inverse is the range of the original function, and the range of the inverse is the domain of the original function. So, since the domain of the original function being b to the x, the exponential function, is all real numbers, in other words, minus infinity, infinity, the range of the inverse function here, of course, being log base b of x, is minus infinity, comma infinity. Now we can also determine the domain of the logarithm function. Here we've determined the range of the logarithm function. The domain of the logarithm function the domain of log base b of x, that's going to be the range of b to the x, and if you recall, the range of the exponential function is the positive numbers. So the range of b to the x is 0, infinity. So the domain of the inverse, which is log base b of x, is 0, infinity. Practically, what that means is you can't take an x value less than or equal to 0 and put that into the logarithm. So we can't do something like log base b of -1, for example. That will give us no output. So those are some of the main ideas of the logarithmic function. So we know that it's the inverse of the exponential function. We have this statement here that of the equivalence between a logarithmic statement and an exponential statement. And we have the domain and the range.